Good morning, everyone. Today we are going to work on the load flow problem. And although some of you may be familiar with what is a load flow problem, we will go deeper into the details because we wanted to numerically solve the load flow problem. So in the laboratory that you are going to do next Friday, you will be asked to write a load flow solver yourself. Okay. And this is not because we wanted to stress you, but because this solver for the load flow problem, it's used in the set estimation. So I need you to have a good understanding of how to solve a load flow problem because it's propedeutical for the set estimation problem, which is our ultimate goal of this part of the course. Okay, so that's why the title of the lecture is Numerical Solution of the Load Flow Problem. So nevertheless, I want to introduce the load flow problem for those of you that are not familiar with this kind of a fundamental problem of power systems. So that's the outline of the lecture. It's a pretty rich lecture, as you will see. So there is an introduction where I will focus essentially on the problem formulation and the working hypothesis that we are using to formulate the load flow problem. Then we'll formulate the load flow in Cartesian and polar coordinates. They are slightly different, these two formulations. They're very peculiar, and there are advantages and disadvantages that we try to analyze. Then we'll show how to formulate to compute the line power flows, and finally, how to write a solver, a numerical solver, via the Newton-Raphson technique. Okay, because load flow is a nonlinear problem that has to be numerically solved using these kind of approaches. Introduction. Now, until now, we have seen this. We have just seen how to write the equilibrium of a power grid using nodal voltages and nodal current injections absorptions. Okay, so essentially the admittance matrix formulation of the balance of a power system considers only currents and voltages. So essentially is the ensemble of the Kirchhoff laws. Okay. Now, is it this formulation usable from an operational point of view? Let's suppose that you are a grid operator, you're a Swiss grid, okay? And you're sitting in the control room. What are you imposing in the boundaries of your system? Currents and voltages or something else? What do you impose in the nodes of the system? Let's suppose that you are sitting in the control room of Swiss grid. Yeah, exactly. So you're fixing powers. You're not fixing currents. Okay. When the electricity markets, for instance, are reaching a given equilibrium of the various biddings, what they bid, it's energy scheduled each 15 minutes that then translates into power. So that's why this formulation of the equilibrium of the system is not very much practical to be used. Okay. So I remind you that we have a network with S nodes, therefore we have S complex voltages and X complex node currents linked by S equations that are essentially the internal constraints which are fixing the link between voltages and currents. But again, this formulation is not very practical. Nevertheless, we will make use of this formulation to write the load flow problem. So this set of equations represents what we call internal network constraints. So are the equalities that you have to obey to solve, to determine an equilibrium point of your grid. Okay. So in terms of number of variables, how many variables we have? Well, we have 2S complex voltages and currents, which are equal to 4S real variables. Okay. And we have two S linear equations, which are represented by these equality written in matrix form. Therefore, we need to fix two S real variables to get the other two S real variables. Okay, irrespectively if you're using voltage and currents or powers. Okay, so these are the number of degree of freedom that you have in the system. Now, from the 4S real variables, 2S can be fixed arbitrarily, let's say arbitrarily depending to the operational needs of the system, and the remaining 2S can be computed using, for instance, these set of equations. But we will see that we're not using the Euclid admittance matrix formulation. So when we solve the system by fixing 2S variables, we can compute everything. We can compute active and reactive power injections. Again, if you're using the admittance matrix, okay, we can compute the branch powers and branch currents, namely the currents that are flowing through the lines or the powers flowing through the lines at the two terminals of the lines that are not necessarily equal. The losses of the system, active and reactive power losses, and if we essentially impose in a system external constraints related to voltage and currents, we can determine all the rest of powers. But again, as I said, this is not very practical because we cannot impose phasors of currents, okay? At least in power systems. In power electronics, yes, you can do that, but in power systems, we are not very comfortable in imposing phasors of currents, of nodal currents. So as I said, in practice, the operating conditions that are imposed in power grids are not imposing currents, but rather powers, okay? For many reasons. As I said, when you are, for instance, establishing what we call dispatching plan of power plants, so essentially you establish a trajectory in power in the next 24 hours for a given power plant, you impose powers, you don't impose the current that the power plant will inject into the system. You impose the power that this power plant will inject into the system. Okay. When you are, for instance, forecasting what a PV plant, a photovoltaic plant, will produce in the next 24 hours, you forecast power, you don't forecast its current. Okay. Additionally, concerning loads, let's suppose that you are against Swiss grid and you need to supply a given node in the system that is a load. Okay, it's a city. Let's suppose the city of Lausanne. So load buses, normally in load buses you are imposing active and reactive power coming from historical measurements. Let's suppose that today is Monday. Yesterday evening, by using historical measurements in the control room of Swiss grid, they knew that the city of Lausanne should absorb a given profile in the next 24 hours. This is due to the fact that load is highly forecastable. So it's pretty straightforward to forecast what is going to be the absorptions of an aggregation of loads in a given day of the week. Okay, there is a bunch of literature that studied how to forecast this quantity. So that's why in load buses, typically you impose active and reactive power. So they're typically fixed by quantities that we call Pi star and Qi star. Now, in practice, it is quite inappropriate to represent the loads by constant admittances or constant power absorptions. So normally, when you're fixing the powers, you have to unlock the voltages because you are fixing two quantities in the node, okay? Because if you are fixing also the voltage, you are fixing also the current. So you can fix only two variables in a load. So you fix typically active and reactive power. Now, if you fix the active and reactive power, the voltage will be a result of your computation. Now, if you fix active and reactive power, you have to know that the power that a given load is absorbing is a function of its voltage. Okay? For instance, aggregation of asynchronous motors that absorbing active power with a slight dependency on the voltage, gas discharge lamps, etc. So all the loads that are inside a given pot, let's say the city of Lausanne, when you move the voltage, they slightly change the amount of power they absorb. Okay, so fixing the power in a load to fixed quantities, Pi and Qi, is not truly exact, not truly correct. So normally you take into account this dependency by these two equations, where essentially you say the power that I'm going to absorb is equal to P0. So for instance, for the active power, P is equal to P0. So P0 is a constant value times an exponential function of V over V0 to alpha P. So V is the voltage which is resulting from the load flow, and V0 is the rated value of the voltage. Alpha P is an exponent that you may fit according to the load that you are supplying. Okay? So this means that you can incorporate this nonlinear equation into the load flow. Okay? The same thing applies to the reactive power. So this is what we call exponential load model. Okay? This means that you can fix P0 and Q0, but then you have to bring in the load flow problem, these two equations, since they will slightly change the active and reactive power that they are going to absorb, different from P0 and Q0, according to the voltage that you're going to get into the solution of the load flow problem. Okay? So to recap, in the load buses, we fix active and reactive power. Okay? What do we do in the generator buses? So in the buses where you have something which is injecting power. So normally in these buses, you fix the active power. Again, this is due to the fact that in the equilibrium of the system, given by a market, for instance, the profile of power that is going to be injected by each power plant in the next 24 hours is fixed, is given by the clearing of the market, actually. Okay? So the P, the power that your generators are going to inject in the next 24 hours, is known. Now, it's very convenient to fix also the voltage, the module of the voltage in the generator buses. Okay? Why? It's convenient to fix the module of the voltage in the generator buses. Intuitively. Why? You're, as a power systems engineer, you tend to fix the node, let's say the voltage in the generation buses. So you are solving a nonlinear problem, okay? You will see in a while how complex is the load flow problem, okay? When you are solving this nonlinear problem, you are getting one of the possible solutions. It's a problem that have multiple solutions in general, okay? Now, out of these many solutions that you have, you want to pick those solutions that have a technical sense. Namely, they represent a feasible state of the system. Okay? The voltages of the system, they should be kept as much as possible close to the rated value. Okay? They cannot change. They should not change. This is due to various operational aspects related to the insulation of the system. Therefore, if you fix the voltage in the generation buses, you get a solution where the voltages are in principle closer everywhere to the rated values. So that's why in the generation buses, you tend to fix the voltage and not the reactive power. Okay, this is written here. So essentially fixing the VI in the generation buses rather than the reactive power is very convenient for various reasons. So fixing the voltage, typically a value which is closer to the rated value, normally between rated value Vn and 1.1 Vn, Vn is the nominal voltage, means that we set the voltage in the network key points. The network key points are essentially the generation buses, is where you are imposing the voltage. And this means that when your load flow converges, it converges to a solution where the nodal voltages everywhere, not only in the generation buses, are closer to the rated values. Okay, so I facilitate the identification of a solution that has a technical meaning. Okay, because otherwise you will get solutions that are completely crazy. Additionally, in the generation buses, the generation buses are built to keep the voltage fixed. For instance, a synchronous machine as a system that is into the machine that tries to keep the voltage fixed at the terminals of the generators. So also physically speaking, imposing the voltage does have a technical meaning. Okay? If you are an operator of a nuclear power plant, the machines in the nuclear power plant, they have a regulation system that tends to fix the voltage at the terminals of the machines. Okay, so that's why fixing the VI star does have a technical meaning also from the operational point of view of the power plant. The reactive power is a consequence of the computation. So we fix the active power PI star and the voltage VI star in the generation buses. Of course, the Q is a consequence. Is a consequence of the computation, the reactive power. So this means that, this is just a note, the reactive power of the generators can vary between a minimum and a maximum value of the machine. So this means that when you are solving the load flow problem, it can happen that the reactive power that a generator is asked to inject due to a result of the load flow can be outside the limit of the machine. So a given generator cannot inject a reactive power whatever. This reactive power is constrained between a min and max limit given by the technology that you are using in the machine, and therefore is a quantity that has to be strictly constrained. How to deal with that we'll see in the laboratory. Okay, now, so we have justified that for both load and generators it's convenient to fix the active power. Okay, now, so you have a kind of cloud is your grid. You're fixing active power in the generation, in the load buses, and in the generation buses. You're fixing reactive power in the loads and voltage magnitude in the generation buses. What does it mean? It means that you're fixing the active power in all the nodes, right? Now, is this technically feasible? Well, actually, no, because if you're fixing the active power in all the ports of the system, it means that you are arbitrarily setting the network losses, which is clearly absurd. Because the losses in the system are a consequence of your load flow computation. So if you fix the active power everywhere, most likely your solution will be impossible. You cannot solve the load flow problem because you are a priori fixing the losses in the system. Okay. Now, since this is not possible, what you have to do is to unlock one of the generation buses. So you have to choose one of the generation buses where you don't fix the active power. okay? You fix only the voltage in this node. So this generator is called slack bus, okay? And in this generator, essentially you fix the amplitude of the voltage and the phase of this voltage. And you arbitrarily set the phase of this generator voltage equal to 0. It means that all the phases of all the other phasors, currents, voltages, powers, and whatsoever, are referred to this guy, to the slack. Okay? This is how we traditionally formulate the external constraints in the load flow problem. Okay? Normally, the slack bus is in a physical system. So let's suppose that you have a closed power grid. Let's say a closed power system, an island, let's say, is typically the largest power plant you have into the system. Okay? Just to give you an idea of how to pick the slack bus. So, indeed, as I wrote here, the slack bus can be selected as a generator where there is a significant amount of power installed. In this case, as I said, the phase of the voltage is fixed to 0 because you still need to fix two quantities in this node. So we said that we cannot fix active power. We said that we cannot fix reactive power because it's a generation bus. So you have to fix two quantities. What you fix, the voltage module and the voltage phase for the slack. Okay? So again, is our reference to for the slack bus voltage phasors. Now, just to sum up, so we have these are the external grid constraints, okay? So in the generation buses, we fix active power and voltage amplitude, and what we determine are the reactive power of the generation node and the argument of the voltage in the generation node. In the load buses, we have active and reactive powers fixed, and we determine the voltage module and the argument of the voltage module. In the slack bus, we fix the voltage amplitude and its argument equal to 0, and we determine active reactive power injected by this guy. Okay? So this is the set of the external constraints into the grid. Okay? Which are the internal constraints? So these are the constraints on the nodes, on the external nodes of the grid. The internal constraints are given by this guy, by the admittance matrix. So if you put together internal and external constraints, you put them together, you obtain what we call the load flow problem. That can be solved via the Newton-Raphson method. Okay. Clear? Okay, these are the ingredients of the recipe. Now let's try to formulate the load flow problem in Cartesian and polar coordinates. Let's start with the Cartesian coordinates. So in Cartesian coordinates, our variables, as well as the parameters, are expressed using a Cartesian notation. So the voltage phasor in a generic bus I, so VI upper bar, is written as VI prime plus J VI second. So this is the voltage of the eth node. So same notation for the voltage phasors in the lth node. So the generic element IL of the admittance matrix Y is GIL plus JBIL. Okay? Now, I don't know whether you paid attention, but here in the load flow problem formulation, we get rid of the currents. So essentially in the load flow problem, we are writing everything in terms of powers and voltages. Okay? Why that? I repeat again. Powers, because they're essentially according to the operational aspect of the market and the dispatching. Voltages, because the voltage in the system, they have to be constrained to be as much as possible close to the rated value. because of the insulation of the system. So that's why we fix these two quantities. Yes?
I have a question regarding the rated value and the VI star.
Mhm.
Is it the same thing or it's different?
Yeah, so normally what you do, um, let's make me an example. Um, I know that you didn't follow my course in power distribution systems. Normally, all the equipment of a power grid are rated for a specific value of voltage. Okay? So this means that a given equipment, a breaker, a line, a motor, even your laptop when you connect it to the power plug, is rated for a specific value of voltage. Okay? It means that in the insulation in the equipment is designed to withstand a given amount of voltage. You cannot go below or above this voltage. Typically, the bandwidth within which the voltage can move is plus minus 10%, just to give you a very rough number, okay? So this is telling you that each layer of the power grid, let's say low voltage distribution, medium voltage distribution, sub-transmission and transmission grids, they have all the equipment that can operate in a very restricted band of voltage. That's why you fix the voltage, and that's why normally when you solve the load flow problem, this V is the rated value of the voltage in that part of the grid. Okay? Normally you tend to fix it to the rated value of the voltage. Okay?
And the VI star is the same.
Yeah, correct. Okay? So, of course, you can, due to operational considerations, slightly move the V. Okay? You can slightly move the V because you know that by increasing the V in a given node, these have a beneficial effects for the rest of the grid. But still, it has to be constrained within the bounds of the voltage that are acceptable for the system. If in your solution you get voltages in the loads that are outside plus minus 10% the rated value of the voltage, the solution that you get is technically unfeasible. It is an equilibrium of the system because you determine the equilibrium of the system. However, technically speaking, you cannot deploy this solution because you are outside the operational bounds of the system. Okay. Now, as I said, we formulate everything in terms of powers and voltages. So we cannot use the admittance matrix as is. So what we do, we have to translate essentially the admittance matrix into powers. Now the complex power SI that you inject or absorb in a given node I is PI plus JQI, can be written as VI upper bar times II underbar. II underbar is the conjugate of the current. That's the classical definition of power. So what I do is that since we don't like using the currents, I just replace the II underbar, so the conjugate of the current, with the eth row of the admittance matrix. Okay? So I have here below SI equal to VI upper bar times, you see this guy? This is the eth row of the admittance matrix. Okay? So it's the sum from 1 to S of the YIL VL. Okay? Now I replace in this equation the the Cartesian formulations that I used for the voltages and the admittances. So I have here the VI expressed as VI prime plus J VI second times the sum from L going to from 1 to S of the GIL minus JBIL. Minus is because this guy is conjugate, okay? Times VL prime minus JVL second. Again, minus because the voltage is conjugated. So this guy gives me the equality constraints of the load flow problem in Cartesian coordinates written in terms of powers and voltages. I don't have any longer the currents here. So I take the real part of this product and the imaginary part. So the real part is the active power injected in node I, so is equal to this combination of these two sums. And the Qi is the reactive power injected into the node I, again, is the imaginary part of the previous equality. What are these two equations? These are the equations of the load flow. How do you use them? You use them into the first equation, you use the first equation in the generation buses and the load buses, because Pi is the fixed into the generation and load buses, and use the second one only in the load buses, because you fix the Q in the load buses, we said. Okay. For the voltages, we said that we fix the voltage in the generation nodes. So the voltage, it's very simple. You just fix the module of the voltage, the square of the module, Vi squared equal to Vi prime squared plus Vi second squared, where in the generation buses and in the slack. Okay? So these are the set of equations that I'm using in polar coordinates. So this is the ensemble of the load flow problem in Cartesian coordinates. So for the slack bus, I have Vi second equal to 0. We said that in the slack bus, we fix the voltage angle. In Cartesian coordinates, fixing the argument of this voltage equal to 0 means that its imaginary part is equal to 0. So Vi second is equal to 0 for the slack bus. Then for the G generators and the slack bus, you see here, for the G generators and the slack bus, we fix the module of the voltage. Let's say the square of the module of the voltage. Okay? Then in the G plus U nodes, where G are the generators and U are the loads, I fix the active power and of course the link with the voltages. And in the G plus in the U nodes, essentially the load buses, I fix the reactive power. This is the load flow problem in Cartesian coordinates. As you can see, is a nonlinear problem. Okay? It means that when you solve it, essentially by fixing Vi star, Pi star, Qi star, and you determine all the other free variables, you can get many solutions of that stuff. You can also have an unsolvability problem. It means that if you fix some initial values, it can happen that your load flow problem does not have a solution. Okay? It means that your system cannot transport powers if you fix a given set of boundary conditions. Okay? How many equations we have? Well, we have 1 for the first equation, G plus 1 plus G plus U for the second, plus U for the fourth set of equations. And if you sum them up, it's equal to 2S. So it's exactly the number of equations that we need to have a well-constrained problem. Okay? Polar coordinates. In polar coordinates, it's even easier, the formulation. So essentially, instead of using the rectangular formulation of my state variables and my parameters, I use the Euler notation. So essentially, I say Vi upper bar is equal to Vi module times e to the power of j theta I, where Vi is the module of the voltage in the node I, and theta I is its argument with respect to the slack bus. The same thing I do for the current. II upper bar is equal to II times e to the power of j phi I, where phi I is the phase of the current phasor injected into the node I. And the same story is for the IL element of the wide admittance matrix, where YIL capital letter is the module and gamma IL is the argument of the generic element of the admittance matrix. Again, I write the power, the complex power S, injected or absorbed into the generic node I as Pi plus JQi, I can write it as Vi upper bar times II under bar, so the conjugate of the current. So here I rewrite essentially what I had before in the rectangular formulation. So Vi upper bar times, instead of the current, I'm using the eth row of the admittance matrix. And here what I do is that I'm just replacing the polar coordinate formulation. Okay? So here what I have is the multiplication of all the modules of voltage Vi, admittance YIL, voltage VL, times E to the power of J of theta I, which is the argument of Vi, minus theta L minus gamma IL. Why minus? Because YIL and VL are conjugated. Okay, so that's why you have the minus theta L and minus gamma IL. That's very easy. Now, what's the real part of this SI? Is the active power. So it's the sum of VI, VL, gamma L cosinus of the exponent of the Euler number. So theta I minus theta L minus gamma IL. And the reactive power is the sum of VI, VL, gamma L sinus of the exponent of the Euler number. Theta I minus theta L minus gamma IL. So it's very straightforward to derive the Cartesian coordinate formulation of the load flow problem. So to sum up, the load flow problem in polar coordinates, it's very straightforward. For the slack bus, so for I equal to S, so we have theta I equal to 0. So now I don't have a real and imaginary coordinate part of my variables. I have module and argument. Okay, these are my variables. So theta I equal to 0 is my slack bus, is my reference. Then for the G generators and the slack bus, I just have an identity. I have the module VI star that I fix in these nodes is equal to VI. It's very straightforward, this equality, right? So I say the generator voltage is equal to what I set. Okay, that's very easy. So in polar coordinates, what is happening is that you are shrinking the number of equations because these are trivial equalities. Okay, there is a ticket that you are paying. There is a check that you have to pay, namely that these two equalities, they have trigonometric functions, so they're a bit nasty to let them converge. Okay, so it's true that you are shrinking the number of equations, but still you have these guys that are playing a role in the nonlinearity of the system. So Pi star and Qi star are the powers that active and reactive power that you fix active power into the G generators and U loads, and reactive power only into the U loads. Okay? And these are the equalities that we just derived from the load flow equilibrium. Number of equations is the same. Okay? So it's still equal to 2s. Okay? Voila. These are the two formulations. So just few observations for the polar coordinates formulation. In this case, the first G plus 2 equations. So essentially the theta I for the slack bus and the voltages for the slack and the generators are directly imposing the values of the external constraints. They are trivial equalities indeed. So the number of the equations that is needed truly to solve the load flow problem is compressed, is equal to G plus 2U, as I told you. So you are reducing the number of equalities. However, this does not necessarily imply, as is written here, that a reduction of the computational time is associated to the polar coordinate formulation. This is because the equalities that you get for the active and reactive powers, they contain trigonometric functions that may exhibit more difficulties to converge. Okay. Just a final remark. It exists what we call a hybrid formulation. Okay. The hybrid formulation uses the polar coordinates for the voltages and Cartesian coordinates for the admittances. Okay, so you see that here you use the polar coordinates for the V, and when you're expressing active and reactive power, you're essentially using voltage in polar coordinates, and the G and the B, which are essentially the real and imaginary part of the admittance matrix, you use the rectangular coordinates. Okay, it's another way of formulating the problem. Still, it belongs to the polar coordinates formulation. Okay, you can, yeah, we will see how the Newton-Raphson method can be written for this kind of formulation. Okay, so this is for the moment the problem formulation. Then we will see other peculiarities like the line power flows, and most importantly, the use of the Newton-Raphson method. Now let's make a break. Once we have solved the load flow problem, it means that we have determined the state of the system. So it means that we know voltage everywhere, powers everywhere injected and along the lines. Now, the question is, how can we compute the line power flows? That's a very straightforward computation. So if you remember the structure of the admittance matrix, so the structure of the admittance matrix of the generic node II, so we have the II, which is the generic current injected by your generator or your load, and VI being the complex phasor. Let's suppose that you wanted to compute the flow of power and current between node I and node L. So it's very simple, because since you solve the load flow, you know the phasors VI upper bar and the phasor VL upper bar. In the middle, you just have a pi circuit of known admittances. So computing the power flows through the line, it's very easy. So the SIL, so the power flowing from node I to node L, which is PIL plus JQIL, it's simply equal to the power flow in this point. Okay? Now, which is the power flowing from node I to node L observed on the node I? Because of course the power flowing from node L to node I is different, is a different guy. So which is this power? Well, it's simply equal to the current IIL times the voltage drop VI minus VL, and indeed you have this is the voltage drop through the impedance, so VI underbar times VL underbar times YIL underbar. So this is the conjugate of the current flowing through the line, through these admittance here, times VI. So that's the definition of power, plus the power which is flowing through these shunt admittance. Okay, so the power flowing from I to L is equal to the power flowing through this admittance plus the power through the longitudinal admittance plus the power flowing through the shunt admittance IIL. And the power flowing through this shunt admittance is straightforward, is just VI squared times YIIL conjugated. Okay, so this is how we compute the flows of power through the lines. If you write this equation on the port L, pay attention that you get a different formula. Because here the voltage will be VL, okay? And here it will be VL minus VI, and this will be VL squared. So the flow of power from I to L is not the flow of power from L to I. Okay, don't make this trivial mistake. By the way, if you compute SIL and SLI and you do the difference between these two guys, which are different, what you get? Again, you compute SIL and SLI. We said that they are different. If you sum them, what you get? For the line IL, you sum the two powers at the two nodes. What are you getting? The losses, active and reactive. Okay? In the same way, if you sum all the powers in all the nodes of the system, you sum all together the powers in all the nodes, what do you get? You have the network, okay? Represented by the admittance matrix, all this guy. You sum all the S in all the nodes, you get the losses of the whole system, active and reactive. Okay? It's just the first principle of thermodynamics. You have a closed system where you force the flows of energy everywhere in all the ports. The sum is equal to the losses. It's a conservation of energy. Okay? Now, how can we write this power flows SIL in polar and rectangular coordinates? Well, it's very trivial. So SIL, we just get the formula that we just wrote, and we replace the complex numbers, voltages, and admittances in polar coordinates. So we have VI times e to the power of j zeta I. That's the polar expression for VI. So we have the complex conjugates for the same voltage. You see that there is the minus theta minus e to the power of minus j zeta I, and the same thing for the VL, and then all the rest is coming straight forward. Okay, so that's the polar expression write up for the SIL. Okay, so here gamma I is the argument of the admittance YIIL. Theta I and theta L are the arguments of the node voltage phasors. Okay. Now, still for the line power flows, how can we formulate them in Cartesian coordinates? Well, we just get the SIL, so the PIL and the QIL, so which are the real and imaginary part of this product, and we just replace the G's and the V's written in Cartesian coordinates. I mean, again, it's pretty straightforward. So these are the PIL, the QIL. These are auxiliary quantities which are coming out of the solution of the load flow. They are just a consequence of the load flow equilibrium. You can also write the flows of power, active and reactive, using a mix of polar coordinates for the voltages and Cartesian for the admittances, as we have seen in the load flow problem formulation. It's an alternative way of computing the flows of powers. Again, pay attention, PIL and QIL are different from PLI and QLI. Okay? Now, you have all the ingredients of the load flow problem. So we have formally wrote the load flow problem in, again, Cartesian and polar coordinates. Now the question is how we solve it. Okay? How can we solve it? So there are plenty of methods that we can use. The one that I'm going to illustrate to you is the adoption of the Newton-Raphson method. So NR stands for Newton-Raphson. I will recall you briefly how the Newton-Raphson method works, and then we will write the load flow problem using the Newton-Raphson method. Now, as you may have observed, the equations which are linking the network quantities, voltages, powers in particular, are nonlinear in either polar and Cartesian coordinates. Okay? And also in the mixed coordinates formulation, they are still nonlinear. So what you do is that you have to adopt let's say a solver, for instance, the Newton-Raphson method, and you have to fix the value of the unknown variables to values that make sense. So I remind you that these problems, they have multiple solutions. Okay. Now, ending up in one of these solutions depends on the initial values that you are setting for the unknown variables. We'll clarify this in a moment. So what you have to do is that you have to fix an initial reasonable profiles of the unknowns. For instance, just to give an example, For the unknown amplitudes of voltages, for instance, you can set them to 1 in per unit. So you say, in the nodes where I don't know the voltages, I set the initial value equal to 1 in per unit. And for the unknown phases, I can set them equal to the phase of the slack bus, for instance, 0. Of course, as a function of these initial values, you can end up in one solution of the problem or into another one. Okay? So the tricky thing here is that the solution that you are obtaining should have a physical meaning. Physical meaning means that the voltages have to be within the bounds and the line currents have to be below the ampacity limits. If you don't have these two conditions, essentially your grid cannot work. Okay? The solution that you get has no technical meaning. Now, how do you check that your numerical solver has reached a given solution? Well, essentially what we do is that we control the residuals of active and reactive power, and when this the value of these residuals it's diminishing, is below a given threshold, we say, okay, with a given tolerance, we said that we obtained a solution. I will clarify this concept in a moment, okay? Now, let's recall the interruption method. It should be already in your technical background. So let's suppose we have a given differentiable, that's a fundamental property, nonlinear function of x, say f of x. Okay? Are our load flow equalities differentiables? If you check them, they are in both a polar and the Cartesian coordinates. Okay? So we do satisfy these fundamental property that we have to have for the application of the interruption method. Okay, now we have a function f of x, for instance, our load flow equalities, and we want to determine the value of x, let's call it x star, okay, so that the function f of x has a given fixed value y star. Okay, so in our load flow problem, y star are the values of the fixed boundary conditions, powers, both powers in the generation nodes, powers in the load nodes, rated values of voltages in the generation nodes, and so on and so forth. And the x are the unknowns. Okay, so essentially the variables that are computed by the load flow problem. So x star actually is unknown. So our goal is to find x star. So I wanted to solve these, I have to satisfy this equality, f of x star is equal to y star. Okay, that's our problem. F is nonlinear and differentiable. So we start with an initial guess of our unknowns, let's say x of 0. So this is the famous initial profile, okay, of the unknown values. Okay, it has to be fixed to something. So normally, I mean, this looks like a trivial problem, okay? But I'll give an example. If you want to solve the load flow for the European transmission grid, the European transmission grid has several thousands of nodes, okay? Fixing the initial profiles that has a technical meaning, that gives you a solution that has a technical meaning, is not a trivial exercise. Okay, so if your network has 3-4 nodes, okay, normally you can do even a brute force kind of study of your system. But if the number of nodes is of several thousands, it's not so easy. Okay, if you look at, for instance, at the distribution grid of the city of New York, the distribution system of the city of New York has more than 6,000 nodes. It's called also the matrix. Okay, solving the load flow for this grid, it's not so trivial. Okay, especially for the selection of the initial profiles. Anyhow, let's go back to our problem. So we fixed the initial value of our unknowns. So x0. The unknowns, I remind you that for the generation buses are the reactive power and the magnitude of the voltage. And for the load buses are the real imaginary part of the voltages. So we indicate delta x0 as the difference between x star and x0. Do we know delta x0? Do we know delta x0? No, we don't, because we don't know x star. Okay, x star is our unknown. Okay, but we can write an approximation of this delta x0. So how we do that? Well, essentially we develop in series of Taylor f of x. So f of x0 plus delta x0 is equal to f of x0 plus df over dx computed in x0 times delta x0 plus the second derivative of f over dx squared computed again in x0 times delta x0 squared over factorial of 2 and so on and so forth. Okay. Now we make the hypothesis that the value x0 is sufficiently close to x star. This is not necessarily true, but this is our working hypothesis. Okay, so if this is true, I can write f of x star, which is essentially f of x0 plus delta x0. If you sum them up, you get f of x star, as f of x0 plus only the first term of the Taylor expansion. Okay, of course it's a circa here. Okay, now if I change the way I'm writing this equation, so I can write it as, so essentially write f of x star minus f of x0, I get my y star, and I can refactorize the equation in this form. So f of x0 plus df over dx computed in x0 plus times delta x0 equal to y star. Now, in this equation, I know everything except delta x0. Y star is given, are my external constraints. F of x0 is given because I can compute my load flow equations in x0, which is my initial guess. The df over dx is known because my equation, my f of x is differentiable, so I can express df over dx. So the only quantity that I have to compute is delta x. Of course, delta x0 is not exactly equal to the true one. Why? Because I have removed all the other Taylor expansion terms of order higher than 1. So this delta x that I get, it's an approximation, a good approximation of my true delta x0. So I will call it delta x1, which is computable. Okay? So all these quantities here are known. So what I do is that by using this delta x1, I can recompute my, let's say, a new value of my f in x1, where x1 is equal to x0 plus delta x1. So here I can compute the residual, delta y0. But what is interesting is that I can compute an x1, which is equal to my initial value x0 plus this delta x. Now, by getting x1 allows me to compute again the df over dx in x1, the f of x1, and I go on. So I can iterate this, this formula for many iterations that are going on forever, essentially. Okay, so I can generalize this method for the nu plus 1 iteration. So I have that the x of iteration nu plus 1 is equal to x nu plus delta x of nu plus 1, where delta x of nu plus 1 can be computed, pardon me, the x nu can be computed using the equations that we just saw. So I can make the method iterative. Now, these two write-up of the iterations are for different values of y, of y star, which is my external constraint. If y star is different from 0, I write it this way. If y star is equal to 0, I write it this way. But that's just a, just a trivial aspect. Now, can we interpret this from a graphical point of view? Well, yes. Essentially, let's suppose that this is my f of x, okay? And I suppose that my y star is equal to 0. So essentially, I wanted to find this root of my equation. I want to find this x star for which f of x is equal to 0. Okay? So I start from x0. Okay? I compute my f of x0. I compute the df over dx, which is this tangent here. And the equation that I showed you before allows me to compute x1. In x1, I recompute f of x1. I compute the df over dx of x1 that allows me to compute x of 2, and I keep going until I reach the x star, and I compute a good approximation of delta x0. Okay? That is what we call method of the tangents, or Newton-Raphson method. When I stop the method, what should I satisfy? Well, essentially, I can have multiple criteria to stop the Newton-Raphson method. So one of the criterion can be that my residuals, delta x and delta y, are below a given threshold. One of them or both of them. Okay? Because when I get a solution, it means that my residuals are becoming infinitesimally small. Okay, so it's up to me to set a threshold, for instance, on the delta x here, or on the delta y, to say, okay, I reasonably enough close to the root of my f of x, so I got my solution. Okay, so normally I can set delta x lower than a threshold, or the residuals on the delta y below a given threshold, where epsilon is a tolerance. Okay. There is a slight variant of the Newton-Raphson method, which is described in this graph here. You see that here in x0, I compute my tangent, that the tangent is bringing me into x1. And then in x1, instead of recomputing the new tangent, I keep the tangent that I computed in x0. So I don't recompute the df over dx. I keep the tangent the same. You see? Tuck, 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 tuck. Why I do that? Because you see, the x, 2, 3, 4, etc., they proceed slowly compared to the recomputation of the new tangent. Why should I do that? Why I can keep the tangents constant? For computational reasons, because I don't have to recompute them. Because if your system of equations has 5,000 equations, recomputing the df over dx, which is a Jacobian matrix, can be computationally pretty intensive. Then what you can do is to intentionally choose to not recompute the tangent and keep going with the tangent you computed in f of x0. Of course, it will slowly converge, but you are gaining more time in not recomputing the Jacobian. It's your choice, It's especially for systems with thousands of equations. Okay. Good. Now, let's scale up and let's move to the case of a multidimensional function. I have a function f, one of several variables, x1, xs, and I have s equations. It's like the load flow problem, okay? So I have many equalities for the active, reactive power, maximum voltage, and so on and so forth. And then I have many variables, which are my unknowns, okay? So I have a system of S equations in S unknowns, okay? And I wanted to solve it using the load flow, using the Newton-Raphson method. So in this case, it's essentially the same story. The hypothesis is that the F1, Fs, they have to be differentiable. Okay. So what I get is that I can express my nu plus 1 iteration as the Jacobian matrix of the F with respect to the X. So the Jacobian matrix is formed by the partial derivatives. The rows of the Jacobian are the partial derivatives of the Fi function with respect to the variables x1, xs times the array of the delta x equal to the array of the delta y is essentially how we write the Newton-Raphson method for a multidimensional problem of S equations in S unknowns. So in a compact form, I can write Jacobian J of iteration nu. I remind you that this guy is computed in the solution that I got in the previous iteration, times delta x of nu plus 1, which is my unknown, to be computed, equal to delta y at iteration nu, which is also a known quantity. So in this case, the delta x I of iteration nu plus 1 is equal to, as in the other case, xy of iteration nu plus 1 minus xi of iteration nu. The delta y I are essentially the residuals for the eth function fi. Okay? Nothing special, it's just extension to a multidimensional case. This is how we compute the x at iteration nu plus 1 is equal to the x we got at iteration nu plus delta x that we compute using equation LF24, which is essentially the Newton-Raphson iteration for the iteration nu plus 1. You see that this Jacobian has to be invertible. Okay, if the Jacobian is not invertible, it means that you cannot compute the delta x. So the Jacobian has to be non-singular, otherwise you're in trouble. Okay, so when the Jacobian is getting singular, there are special things happening in the load flow problem that I'm not discussing here because they have interesting implications from the static stability point of view of the system. But we may discuss this, you may discuss this in the course of dynamics of transmission systems with Professor Cherkaoui. It's not the goal of this course. Voila, this is the way you are computing the generic value of the x at iteration nu plus 1 and the delta x as well. So far, so good. Now, the problem we have now is how to write these equations. How to write the Jacobian J, how to write the delta y, how to write the delta x for the load flow problem. How we write this generic iteration of the Newton-Raphson method for a multidimensional problem with respect to the load flow equalities, which is what we're going to do now. Load flow in Cartesian coordinates. Okay? Which are the known variables? Well, we have to split between load buses, generation buses, and the slack. Okay? Now, in the load buses, what do we know? We know the active power P and reactive power Q, which are the unknowns. So essentially, the active and reactive power are the Y. Okay? The unknowns are the real and imaginary part of the voltage. So if you go back to the formulation of the Newton-Raphson method, so essentially you have that the J are composed by the partial derivatives of the load flow equalities. The delta X are given by the residuals on the real and imaginary part of the voltages, and the delta Y are the residuals on the active and reactive powers. And this is what we have. Okay, so these are this is the Jacobian matrix of for the load buses given by the dp over dv prime and dp over dv seconds. So this is the partial derivative of the active power absorbed by the node with respect to the real and imaginary part of the voltage, and same story for the reactive power. Okay, so this is a piece of the Jacobian that we need. So this is my delta x. These are my unknowns, real and imaginary part of the voltages in all the load buses. And this is my delta y. Okay, delta P and delta Q are the delta Ys in the generation buses. So here I'm just recap what is delta Pi, what is delta Qi, what is delta V prime and delta V second. Okay. Now, Pi and Qi, so the expressions that you have here for the Pi nu, Qi nu, and the same expression that they are using to compute this Jacobian, they are known. And if I go back by using this red button, okay, so this is Pi. Oh, sorry. So this is Pi and this is Qi. Okay, so these are my f of x. These are the powers as a function of the voltages. I remind you that the x, the unknowns, are the voltages. Okay, so these are the equations I'm using to compute both the Pi, the Qi, as well as this Jacobian matrix. Now, Jacobian matrix, let's try to compute these block matrices, dp over dp prime, dv prime, dp over dv second, dq over dv prime, dq over dv seconds. So JPR is essentially the block matrix given by the dpi over dvl prime and dpi over dvi prime. So essentially I took the previous equations of the Pi as a function of the voltages, and I just derived as a function of the L and I. I remind you that here I have the node power Pi, and I can derive with respect to the real part of the generic node L or the node itself. Okay, so you have two values of this partial derivatives. Same story when I derive the generic power Pi with respect to the imaginary part of the generic node L or the node itself I. Okay, so these are the block matrices associated to this first row of the Jacobian matrix. Okay. The second row of the Jacobian matrix contains the partial derivatives of the reactive power with respect to the real and imaginary part of the voltages. I use the same process that we had before. Okay, I just take the load flow equations written in Cartesian coordinates, and I just express the partial derivatives of the Q as a function of the real and imaginary part of the generic node L or the node itself I. That's very trivial because they are linear functions, you know. It's very straightforward to derive. Well, let's say they are quadratic functions, so the derivatives, the partial derivatives are very straightforward to be computed. Generation buses. In the generation buses, what do we have? So the known quantities are active powers, P, and voltage module. In particular, the square of the voltage module. Okay, so I have to express the dp over dv prime, dp over dv second, so the partial derivative of the injected power with respect to the real and imaginary part of the voltage, and the module of the voltage squared as a function of the real and imaginary part of the voltage itself. So this second row is very simple to be computed. So I don't write this guy. Why? I don't rewrite the dp over dv second and dp over dv second. Because it's identical to one of the loads. There is nothing changing in the expressions. It's just this guy written with respect to the P of the generators and not the P of the loads. but formally speaking, nothing changes. So I'm not writing it again. Okay. For the voltages, it's very trivial. So the JVR, which is the partial derivative of the square of the voltage of the node I with respect to dVL prime is equal to 0. Because essentially, the voltage at node I is not function of the voltage real part of the node L. They are uncorrelated quantities. Whilst the dVi squared over dVi second is equal to 2 times Vi squared. That's very trivial. And same story for the partial derivatives of the modulo of the voltage with respect to the imaginary part of the voltage. So these are the two sets of the Jacobian matrix which are completing the set of the Jacobian. So this is your problem. So you assemble everything together. So this is your Jacobian. It has the JPR, JPX, JQR, JQX, JVR, JVX times the delta X, which are the delta voltages, real and imaginary, equal to delta P, delta Q, delta V squared. This is the Newton-Raphson version of your load flow problem written in Cartesian coordinates. You just have to replace in these block matrices of the Jacobian the expression that we just saw. See, that's it. There's no more than that. Okay. Let's make a short break. So there is a tiny last chunk of lecture that we have to complete, which is still on the formulation of the load flow problem in polar coordinates. So in this case, again, the external constraints are active and reactive powers for the load buses, and the unknowns are the magnitude and angle of the voltages in these nodes. Not real and imaginary part, but module and phase. So our delta X is composed by an array of delta V's and delta zeta, and our delta Y is composed by delta P and delta Q in the load buses. The Jacobian matrix is composed by 4 block matrices containing the dP over dV, the dP over d zeta, dQ over dV, and dQ over d zeta. Okay. In the generation buses, it's super easy because you have you are fixing only the active power and the voltage. But since the voltage is given, you remember voltage V in the generator is equal to VI star. Actually, this is an identity. So that's why we don't have the other row of the Jacobian. I'm just removing it and embedding this constraint into these equations. I just impose the voltage in the generation nodes to the value that I'm fixing. Okay. So the Jacobian for the generation buses is very simple. It's composed by the dP over dV, dP over d zeta. The unknowns are dV and delta zeta, as always. And the delta Y is just the delta P because the delta V does not exist. V is fixed. So the various components of the Jacobian matrix for the polar coordinates formulation are coming from the, let me go back. Yeah, are coming from the load flow equalities that we wrote before. So these are the load flow equalities for the polar coordinates formulation. So essentially we are using these two equations. Pi is equal to Vi times the sum of the VL YIL cosinus of zeta IL minus gamma IL, and the same story for the Q. So I'm writing the partial derivatives of these two equations with respect to the unknown variables. You see, so the JPV are essentially the DPI over, sorry, the DPI does not want to work. Okay, so the DPI over DVL. So I'm just removing from the summation the VL, so I got only this expression. The same story for the DPI over DVI. So again, I'm determining the partial derivatives of the nodal power injections with respect to the module of the voltage into any other node and with respect to the node where the P is computed. And these are the elements of the Jacobian. And the same thing is for the Jacobian elements with respect to the zeta, where zeta is the angle of the voltage in the nodes L and I. Does not want to work this stuff now. And the same thing, it's with respect to the reactive power injections, with respect to the amplitude of the voltage and the angle of the voltage. Again, these are given. Once you fix the load flow equalities, it's just a matter of computing the partial derivatives. Okay. So to sum up, you put together the equations and you have the JPV, JP zeta submatrices. These are valid for the loads and for the generation buses. And then you have the JQV and JQ zeta, and this is valid only for the load buses. Okay. Your rank knowns are delta V and delta zeta, and your fixed quantities are the P's and the Q's. Okay. This is how you write the generic load flow problem in these cases. So this is the write-up of the partial derivatives of the active power with respect to the nodal voltages and the angles with the mixed polar and rectangular coordinates. Again, it's another way of writing the power flow equilibrium. I'm just reporting it for the sake of completeness. This is for the reactive power as a function of the modules of the voltages and angles of the voltages. And yeah, you can use instead these equations instead of the polar or the rectangular coordinates ones. Okay. Now, in the laboratory that we will do on Friday, it will be asked to you to write a code that solves the load flow problem. Of course, we give you pieces of the code because, of course, it will be too much. But essentially, this code is using the laboratory that you did on the admittance matrix, okay? And it will be asked to you to write a piece of the Newton-Raphson algorithm, okay? Now, in your career, you will not write a load flow code. There are a bunch of softwares that are solving the load flow problem for you, but you need to know how an engine that solves a load flow problems works. Because when you will be sitting in the control room of SwissGrid, you have to know why it converges, why it does not converges, which are the quantities to fix, which are the tolerances to fix. Okay, that's why you need to know how to write the load flow problem to use a given software package. Okay. Anyway, the software package that we are giving you, and you will ask it to complete, is a very nice piece of software. Normally, when I was a student, we were not offered to these kind of things. So use it. Okay, it's a very nice piece of code. It's very solid. We are using it daily in my laboratory for doing research as well. So it's a very nice piece of code. Like the PMU part, you know, the PMU code that you developed. It's a, you know, a commercial level PMU estimation, synchrophasor estimation algorithm. So the software that you have access in this course, it has a pretty high standard for industrial applications. Okay. Now, let's make a very simple example. So just for illustrative purposes. So you have a grid here. So it's composed by 3 nodes. You will use also this grid into the last part of the course to do a optimal power flow analysis. So it has 3 nodes. So it has 3 lines of 50, 100, and 100 kilometers. It's the usual node that we used also in the admittance matrix example that I gave you last week. So you have bus 1, which is receiving active and reactive power injections P1 and Q1 to be determined. So essentially, this bus, the bus number 1, will be the slack bus. Okay. So since it is the slack, you are fixing the voltage equal to the rated value, 240 kilovolts. buses 2 and 3 are two load buses. Okay, so I'm fixing active and reactive power in both of them. Okay, just to give an example, let's suppose that this is the grid of Lausanne. Okay, so you are sitting in the control room of the Lausanne grid operator, which is existing for real. It's in Pierre de Plain. Do you know where is the Chouve? Have you seen that above the Chouve there is a big chimney? Okay, there is a power plant and the control room of the Lausanne grid operator. Okay, so the grid of Lausanne, the 125 grid of Lausanne, has 7 nodes and is fed by Swiss grid in the substation of Romanel. Okay, for those of you that are familiar, if you go to Romanel, there is a huge electrical installation. This is the main connection of Lausanne with the grid, the high voltage grid of Switzerland, operated by Swiss grid. So the slack bus, if you are the Lausanne operator, is Romanel. Okay, because it's the largest, between brackets, power plant. Actually, is the grid of Swiss grid, which is feeding Lausanne. Okay, and all the other nodes are the various nodes where the grid of Lausanne is supplying loads. Essentially, what we call primary substations, supplying the various neighborhood of Lausanne. So if you are the Lausanne operator, you know that the powers that your neighborhood are absorbing in a given time of the day, because you know historically what is happening in these neighborhoods. Okay, so this is why it makes sense to write a load flow problem like this. You have the slack bus, which is in this case, the system supplying you. Is not a physical power plant, but is a system. And then all the rest are PQ nodes, where you fix active and reactive power, either because you measure it or because you know it from historical reasons. Okay. So the 3 lines are characterized by the same conductors. So I'm giving you here the resistance per unit length, the reactance per unit length, and the shunt admittance per unit length in Siemens per meters. So you can write the admittance matrix. Now you know how to do it. Okay. So the nominal voltage of the system is 220 kilovolts. This is the base voltage of the system. Okay. So this is the Y. So we computed the Y. If you look at the Y that I gave you at the end of the last lecture, is the same. And these are is the solution of the load flow. Okay. So here you get the S2 and the S3, which are essentially what you fixed. And these are the voltages in amplitude and in phase that you are getting. Amplitude in actual values and in per unit, and the phase. Okay. I want to show you something interesting. Let me see whether we can show you something interesting. Okay, here you can see the flows S12 and the flow pardon me, here there is a mistake, is S21. This is the flows S13 and this is the flows 31. Sorry, you have to switch this. What can you observe is that S13 and S31, they are not the same, you see? Okay, the difference between these guys in real and imaginary part are the losses in the line 1-3. Okay, same story for the line 2-3. What can you observe if you look at the active and reactive power losses in the line 1-3 and 2-3? What can you observe of interesting? Yeah, the line 2-3 has reactive power losses which are negative. Okay, this means that the line is generating more reactive power than what is absorbing. Why this is possible? Well, this is possible because if we go back to one of the admittance matrix figures. Voila, for instance, this one. Okay, so this is our grid. So each line is composed by a longitudinal element. So this longitudinal element is formed by a resistance and an inductance. So it's absorbing reactive power. And two shunt capacitances. These two guys, these two shunt capacitances, are generating reactive power. When you have reactive power losses in a line which are negative, it means that the reactive power generated by the shunt element it's larger than the reactive power absorbed by the longitudinal element. Okay? Whilst the active power losses are always positive, of course, they cannot be negative because it means that they are generating active power, which is impossible in a passive system. Reactive power losses can be either positive or negative. Okay? Due to these injections of reactive power, it is also possible that the reactive power flows at the ends of the lines, they don't have the same sign. You can have reactive powers that are going to the line, exiting to the line, or going in a given direction, which is the same. Because you are generating reactive power in these lines. Okay, so pay attention when you get these apparently strange solutions of the load flow problem. Okay, let's move on. Voila. Okay, so this is what we get. Let's see what other kind of observations we can do. Well, you see, once you have fixed the active powers, essentially you get everything, okay? So you get the solution, you get the values of the voltages, the angles of the voltages, and then you get the flows, okay? So what your colleague was saying is, what if we get, let's say, bad operating conditions? For instance, the voltage at this node is below the threshold, let's say below 10% of the rated value of the voltage. You have to do something. You have to either change the nodal conditions in terms of active and reactive powers absorbed in your system, or change something into the slack bus, which is increasing the voltage. You have to take counteraction. Okay? So this is how the load flow is used. It's a tool, actually, to understand whether your system is okay or not. Now, a question for you. Do you directly control the flows of powers through the lines? No. What can you control only? Which are the control variables that you have in your hands as an operator? Yes, the voltages and? Or the loads. So you can control the injections. Okay, you cannot control the flows. You can control only the injections. Okay. There are, however, tricks to control the flows on the lines via devices called FACTS, F-A-C-T-S, Flexible AC Transmission Systems. Okay. However, these devices are tremendously expensive, and they are allowing you to directly control the flows through the lines. Normally, if you don't have these devices, you control indirectly the flows through the lines by just controlling the injections. Okay, that's it. All the rest is a consequence. And unfortunately, this consequence is via nonlinear equations. So, you know, when you change, for instance, let's suppose that you have the voltage here in the bus tree, which is too low, okay? And you want to change the injections to get this voltage within the bounds, okay? What can you do? Now let's suppose that you're sitting into the Swiss grid control room. And then you see that the voltage in the bus of Geneva is too low. And you have to take counteractions to bring this voltage within the bounds. What can you do? Let's say, mathematically speaking, you can give me a very precise reply. Let's suppose that you can control the injections. You can do a kind of redispatching of the injections. Okay? How would you do this redispatching? Which is the quantity you have to compute? Again, you have the voltage here in the node number 3, which is too low. And you can control the injections. What do you need to compute? Mathematically speaking, again, it's very simple. Huh? Come on, guys. You need to compute the partial derivative of the voltage at this bus with respect to the injections, right? Do you have this quantity? Yes, you do. If you go back, you see? You have the dP over dV, which is the inverse of this quantity. You have the dQ over dV. So if you invert this Jacobian, you get the dV over dQ and dV over dP. So essentially you get the sensitivity of all the voltages as a function of all the injections. So if you have one of the nodes which is weak, you can say how the voltage will change in this node by changing all the injections everywhere. It's a kind of sensitivity analysis. And this is how you redispatch the other nodal quantities if you have troubles. Okay, that's an example of how to use the Jacobian matrix to compute the sensitivity of a given state variables with respect to injections. Okay. Again, you will see applications of this in the fourth part of the course. Okay. Now let's go back to this system. So this is the solution of the load flow. How you get this solution? Well, it's pretty straightforward. Here I'm writing you the composition of the Jacobian for a polar coordinates formulation. So this is the JPV, JP zeta, JQV, JQ zeta at iteration 0. And here I have the values of all the pivots of the Jacobian for this system of 3 nodes. And this is how you compute delta P and delta Q at iteration 0s, and how you compute delta B, delta zeta at iteration 1. Okay? So this is the Jacobian. These are the delta P, delta Q. Get the delta P, delta Q, and then you go on. Okay? And then you iterate continuously until convergence. Normally, a system like this converges in a couple of iterations. It's super quick, you know. In the exercises that you will do in the lab that you will do on this Friday, you will be asked to develop a Newton-Raphson based load flow engine, and to verify the results, we give you an industrial grade software, which is the EMTP-RV, where the same grid that you have to solve, it's already implemented, and this software can solve for you the load flow. And then you can check whether your code is okay or not. Okay? Voila, this is it.